Hello students, welcome to the IMS Gate Academy. As part of the foundation series, so let's start another session from the operating system. Today topic, in this session I am going to discuss the topic on schedulers, different types of schedulers and dispatcher. From the last class, we have seen the process concepts. In the process concepts, we understand the various activity of a process, like what is a process and program differentiation, and the process states also we have seen. Means process, various process attributes, various operations and a process, and one of the attributes is a process states. The various states of a process we have discussed, as well as the process states transitions and their diagram also we observed. Am I right? So, various process states I mentioned, their activity during this process execution also which we observed clearly. So, just let us continue with this only. Very good evening, very good evening. So, the continue part is that we will see the what types of schedulers are there, what is the activity of a dispatcher, what is the functionality of the dispatcher, we will understand. So, these are the basics, these are the basics for understanding the CPU scheduling algorithms, because after this I will be starting the scheduling CPU or process schedulings. So, for that topic these are the basics only. So, try to stay like a session so that we can learn the things. Okay. So, look at the point here. So, now we are going to understand what the schedulers and dispatcher, schedulers and dispatcher. Okay. So, if you talk about scheduler, what is the scheduler? Please understand, scheduler is again the components of the operating system, its functionality to take the decision, means like you understand, selecting a process from the servicing queue, selecting a processes from the servicing queue and assign to the resource. That is the functionality of a schedulers, and we will see the types of schedulers and each functionality very clearly. So, before addressing into this, operating system maintains a different queues. Operating system maintains a different queues. Okay. Operating system maintains what? Operating system maintains what? Queues. Queues means what? Please understand, the schedulers will work on servicing queue only. Schedulers work on servicing queue means what? It will select a process from this particular servicing queue and assign to the resource. So, what are the queues maintained by the operating system will observe. Getting my point, all of you. So, these queues are maintained by the operating system, like I can say like so these two types of queues you can see, the mainly two types of queues maintained by the operating system. One it is main memory, we call the main memory queues, main memory, and second is what? Secondary memory queues. I hope you are understanding, all of you. Yes, please do respond. Since what I am trying to say, operating system maintains the queues. What is the purpose of queue? From this queue only we select a process. Schedulers will select a process and assign to the resources like CPU or IO devices. Other aspect also will observe. So, main memory. In a main memory again there are two types of queues will be there. One is ready queue. Other is what? Block queue. So, block queue. You have understanding. In a secondary memory, the two types of queues will be there. One is we call job queue. Okay. We will see individually each purpose. Second one is the suspend queue. Suspended queues we can say. Clear all of you. So, ready queue, block queue. So, I can mark it, this is 1, this is 2. Okay. This block queue again classified, two types of queue will be. One is device queue. Okay, device queue. Second one is event queue. Yes, everyone, please respond. So, did you understand? Like the majorly there are 4, we can say like 1, 2, 3, 4, 5 queues I can tell. But in a main memory majorly 2, in secondary memory 2 are there. So, let us observe each one of them. Let's observe each one of them. Okay. In a main memory, the first one is what? Ready queue. Okay, ready queue. Ready queue. Okay, ready queue. What the ready queue containing? So please understand. So ready state is there, right? We have discussed the ready state. Okay. So ready state is there, right? Ready state we have seen. Ready state nothing but the state is implemented by ready queue only. Please understand. So ready queue only. What the ready queue is containing? What is the ready queue containing? List of okay, list of PCBs. List of PCBs. List of list of runnable list of runnable PCBs of processes. I hope you are understanding. So ready, as discussed also, ready queue. So we started ready state is containing the processes or PCBs who are just ready to execute with the CPU, means just waiting for the CPU allocation. Where the new state process get created, once creation happened, the process will eventually move to ready state. What process will not move? For each process when you created, we creating what? PCB. PCB is moving from new state to ready state. So that's what list of runnable PCBs of processes present, which are just literally waiting for the process allocation. So now the queue, I mean this is a queue, right? Ready queue. Queue is contain list of PCBs. Now one of the scheduler will pick a process not the PCB of a process from ready queue and assign to the CPU. I hope you understand this line. Okay, that's what I said. Scheduler functionality to be schedule, it means decision making. When list is like, no, this queue is containing more than one PCB of a process. Now one of the scheduler has to take a decision which process PCB need to be select from this queue and assigned to the CPU state. Like this other functionality also will be there. Clear? Chalo, you write down. So now see, so now this queues are PCBs are maintained, BCBs maintained linked list form. Like you just so to implement this, preferably use circular linked list. Circular linked list is used, like circular double linked list, you can understand. So this is PCB 0, PCB 1, PCB 2, this is a PCB 3. So I also mentioned, like this is a PCB is a data structure having the attribute information of a process. If one of the attribute also link will be there, like you understand here, you can say the state here. So if PCB is having the address of it is pointer available, pointing to or next PCB, this pointing next to PCB, next PCB, like so we forming as a linked list. So preferably that depends on like operating say scheduling queue, like it can be a simple queue or it can be like you understand circular queue, or it can be double linked list, so they can use for implementation. But you understand this connected each other. The PCBs are kept in this queue only. So now schedule will pick one PCB and storing it for execution stage. Is it clear? So first one ready queue is clear, ready queue. Then in the block queue there are two things I said. Second one, okay, second one is the block queue. Okay, block queue. So block queue has of two types, right? Block queue. So what are the two types here? One is what? Device queue. One is device queue. Okay, one is device queue. The second one is what? Event queue. To try to understand clearly, because this will help us to understand other things also. Okay, so device queue and event queue. See, so whenever running process required to perform an IO activity or system call execution, or maybe it may be waiting for an event to occur. So eventually process will move from running state to block state. State we discussed, right? Running state to block state. So now see, the block queue nothing but here block state only. So the block state is like, please observe here, block state is being implemented by block queue, because process goes for IO activity or process goes for some event. Event means what? If there are two processes are there, they are communicating each other. One process sends information to process B, is just waiting for reply from the process B, so that he has to wait. Suppose one process want to execute system call. So now system call should run in kernel mode. By the time this process has to block, you have to wait until system call should be executed from the kernel mode, then the results will come out. So that is an event we can tell. That is a event. Otherwise, you understand, one of the process may request in a shared file, file is not currently available. So, the process has to wait until the file get ready, file is available. So, they are waiting for event to satisfy, right? Yes or no? That is the reason we are splitting again. The block state is again splitting into two things. The block state is implemented by block queue, but it is splitting into two things, device related things and event related things. Sir, how device, what is the purpose of device queue? Please understand. So, devices having many, please observe, like there are many devices, device 1, device 2, so device 3, like let's say device n devices are there. Each device has separate queue, device Q1, so device Q2, so device Q3, so device Qn. So, why each device should have a separate queue? Please understand. Certain moment, more than one process want to use the same device. Such cases, all requests cannot be serviced parallelly. So, they has to wait in the line, they has to be queued. Are you able to understand? The best example I can tell, printer. More than one process may issue the request for printing a file, but all the process print requests cannot be done performed parallelly when we have one single printer. They has to print a line by line, first come first serve, like this, understand. So, we are keeping them, the requests are keeping them into queue. That is the reason every device having separate queue. Whenever such moment comes, they has to be wait in the queue, they has to service the request. Is it clear? Please respond, is clear? Similarly, so more than one process may issue the same event, like suppose there are 3 processes issuing the same system call. The system call eventually should run in kernel mode. So, they has to be run one by one. So, there has to be queue. So, event queue, clear? Event queue, okay? Is it clear? So, this is all the events are we are placing here. Other than the device uses, other events we are placing the processes in this queue. So, now reduced the block state which we discussed in the process state transition diagram implemented by data structure, that is queue, the device queue and event queue. Is it clear? IISc, my dear IISc, is it clear? Why device queue in main memory? Why not device queue? Why not device memory? Why device queue in main? So, I did not understand why not device memory. So, you are talking about why not queue in a secondary memory? Very simple. See, my point is that whenever a program you load from secondary memory to main memory for execution. So, execution may go for CPU or execution may go for IO. Whenever a particular process required to be performed, the IO activity or some other event, this active process, right, that is in the main memory only. So, that in that queue only this has to wait. I hope you understand what I am trying to say. Yeah, right. So, now other thing, third one. What is third one I said? Third one is what? Job queue. So, job queue, this is the secondary memory, right. So, please understand. So, now job nothing but programs, okay, here is a program. Programs are loaded into main memory, okay. So, which are taken from job queue, I hope you understand, okay. Now, job queue contain the list of programs, please. So, job queue contain list of programs which are required to load into main memory for execution. Now, so new state I said, right, new state is nothing but it's a job queue where the programs are going to be converted into process, we are loading them into main memory for execution. Sir, a device also memory. Yes, this device means device also memory. So, I did not understand. Device having memory you are talking? So, please understand, I am just trying to explain you. So, try to correlate. See, example, there are 10 processes are there which you load in main memory for execution. Out of 10, there are 4 processes which are related to IO related, nothing but they want to use a printer. Now, operating system should assign the printer to the process or not. So, that what happened, whenever initially they have some memory related execution, that they will complete CPU activity, they will come for block state. So, they are waiting for in a device queue. Which device queue? printer, for printer the 4 requests are going printer only, we are keeping them PCBs, we are keeping in that queue, so that one by one process they can start printing the file. I hope you understand. Like whatever device process want to use, so the relevant queue they has to wait and complete the service. That's what I want to say. Device memory means, please understand, like a printer, do we have memory? Printer. In a secondary memory you can tell, like secondary memory, we generally our programs in secondary memory only, right? Are you getting IISc? Okay. So now, I hope the job queue is clear. The fourth one is what? Suspended queue. Suspended queue. See, please understand. Under multi-program environment, I discussed a process state transition diagram in which I introduce ready suspend state and block suspended state. So now when you suspend the process, like list of suspended process, it's containing list of suspended processes. Now please understand, the suspended queue contains list of suspended process. You see, whenever any process you want to suspend, you want to send into secondary memory. Now secondary memory in the queue, which queue? Suspend queue we are placing in that one, so that later that you are resuming. Because see, suspension, please understand, I discussed it also, again I am repeating, lack of resources, lack of memory, operating system sometimes suspend some existing process from main memory into secondary memory temporarily, the later again bring back into main memory for completion remaining part. So such cases we are keeping those processes in what? Suspended queue. I hope this is clear. Yes. I am just marking here. We have discussed ready queue, block queue can be device and event queue, job queue, suspended queue. So now all the states from the process state transition diagram which we observed, all are queues only. So like for getting more clarity, so once again I will draw the process state transition diagram with the queues form. Please observe. So we have seen the new state, right? New state. This is a new state which we observed. Please understand. So this new state is nothing but state, that is, but implementation is what? Queue. This is implementation. Getting? Now we have what? So ready state. Ready is there, right? Ready. Okay. Ready state. So ready state is nothing but what? Queue. Which queue? Ready queue. So ready queue. Please observe. Ready queue. Okay. Ready queue. Okay. Ready queue. Now here is a running. Okay. Here is a running. I am marking a circle because this action is performed. Now termination is a action, like we have to terminate the process. So I am marking like this. Clear? Now here is a block. So please understand. Now what we'll do? So process we takes from the job queue and placing into where? Here ready queue, right? Whenever creation process get created, right? We are taking the process from loading into main memory, PCB are loading into running ready state, right? Ready state. Now one of the scheduler, so I mentioned scheduler and dispatch. One of the scheduler will take one of the PCB of a process from the ready queue and dispatch, right? Dispatch or schedule. Please understand. So we call dispatch or schedule. Schedule or dispatch we call. Will dispatch for running state. So now process loaded for executing in CPU is executing. During execution of a process, if the process required any IO operation, so what happens here? It will come, right? For IO activity it will come. Let's take, there is a device is there. So in a device 1 it is waiting. So the process required, many processes may be coming. So initially they has to wait. They has to perform this IO activity. I am marking, So you have to perform the IO activity. Once IO activity is over, please observe. Once IO activity is over, again process has to go to where? Ready queue only, right? Yes or no? Let's take, suppose there is a event queue. Okay, events are many types of events. It can be a system call, it can be anything, right? Now suppose a system call is holding. So now system call is a fork is a system call assumption. So now fork you have to execute it. In once execution IO part, this fork over, child got created, assume that. Child got created, child created, assume that. After execution of the fork, child got created. Again you come back to ready queue. Other than these transactions also I can show you. What are the other transactions? Other transactions are, please observe. Now high priority. So timers. So given time is over, or some high priority process comes. High priority process, high priority. So such cases processes get preemption. Preemption also will happen. Okay, clear? So this is clear. Now this is suppose normal completion. Whenever process execution completed, then we are terminating. So this is a request come for what? IO or any event is occur. Event occur. Okay, occur. Okay. Now this is a transition. Once all IO activity any event is satisfied, it will move, eventually move for ready. So now I am marking this is what? IO or event. Event satisfied. Satisfied. Clear? Is it visible everything? IISc, please respond. Is it visible everything? Now see. So one more state also mentioned. What is one more state? Suspend. So suspend state I mentioned. This is suspend state. Ready suspend. Okay. This suspend nothing but a queue. Please observe. There is a suspend queue, right? Suspend queue. Now process generally from ready queue only, na? From ready queue only. Please observe. From ready queue only we suspend. So we also resume into ready queue. Resume. This is a transition for resume. Okay, resume. This is a transition for suspend. Suspend. Clear? This is a transition. Yes. IISc, please respond. So possible states, possible queues I mentioned. Ready, generally new ready running block termination, right? Which are again implemented by queues only. New is nothing but job queue. Ready is nothing but ready queue. Running state is a state where CPU, in the CPU process executes, and IO activity or other events I shown you, the separate queues are there. So this is a case where a device, more than one process requires same device to be used, so there will be a line in the queue. One by one they come, they use IO. Once IO activity is over, they will go for ready queue. If suppose more than process may issue same type of event or different events. One event is for waiting for other process, one event waiting for some resource. So one event you understand system call to be encountered, like you have to invoke the system call. So there has to be in this queue. So for example I shown one event is what? Fork. So you want to execute the fork system call. You jump from user mode to kernel mode, execute the system call fork, and once child got created, the process has to come back to ready queue for remaining things. Is it clear now? So this is states are implemented by queues here. Queuing diagram you can say. I can say various process queues and queuing diagram. Headline you can see the types of various process queues and queuing diagram. You note it this way. So one other things, preemption part also mentioned, no? Whenever see under time sharing system, every process has to use the equal period of time, equal interval of time of CPU. Once allowable time is expired, automatically it will cause a preemption to the running process. Running process you have to move from running state to ready state. So preemption. Reasons, causes for preemptions are timers are high priority. Also mentioned. Is it clear? Okay. So I hope you understand. So this diagram is much important for us because I want to discuss what queues, right? Sir, schedulers I want to discuss, right? Schedulers works on queues only. Schedulers are works on queues only. So that the discussion can happen properly once we know these things. Yes, IISc, please tell me, is it clear everything? Now, so now move on to the point. So schedulers, we are talking about schedulers. Okay. There are three types of schedulers are there mainly. One is short term scheduler. So let me take it. Long term scheduler. Okay. The one is long term scheduler. Second one is what? Second one is a short term scheduler. Okay. The third one is what? Third one is medium term scheduler. Medium term scheduler. Is it clear? What is the purpose of scheduler? Purpose of scheduler to decision making, right? So decision making means what? Please understand here. One of the scheduler, what a scheduler has to pick a process from some servicing queue and assign to the resource. So the functionality. So there are three types of queues are there. So schedulers are long term scheduler, short term scheduler, medium term scheduler. So now look at this diagram. In the process state transition diagram, presence of schedulers you see. Presence of scheduler now here, please observe, here is up. Okay, here. Ready to running state is there here. So scheduler na, scheduler dispatch I said, right? Scheduler, what is scheduler here? Here is scheduler, short term scheduler will lie here. Clear? I said you na, we have to schedule or dispatch a process from ready state to running state. Who is doing this activity? Short term scheduler. Short term scheduler functionality just pick a process from ready state to loading into running state. That's it. So presence here. Now look at this point. Here is, you look at this point here. So job queue is there, right? From job queue, long term scheduler will work here. So long term scheduler will be. The duty of long term scheduler, pick a programs from job queue, load them into ready state. Will clear. Presences I am showing. Here please suspension. So now from ready state process we are suspending into secondary memory. That is done by medium term scheduler. I hope this is clear. Presence of types of scheduler I shown you. So detailed things we'll observe right now. Clear? So now just talk about long term scheduler. Okay. The first point is functionality. Please understand. Is functionality load programs. Okay. Load programs from job queue to ready queue. Load of programs nothing but PCBs. Please understand. Here is PCBs only we are loading. PCBs have process from job queue to ready queue. This is done by long term scheduler. Okay, long term scheduler. So now see other point. Long term scheduler maintains the important point. Maintains the degree of multiprogramming. So degree of multiprogramming. So please observe many times this point is repeated in the gate paper. So on this degree of multiprogramming. Long term scheduler maintain the degree of multiprogramming. What is the degree of multiprogramming? Please observe. A degree of multiprogramming indicates number of processes available in main memory or number of processes in a system. Example, in certain moment of time 100 processes are there in a system. So degree of multiprogramming 100 done by whom? Long term scheduler. Another moment in the system there are 50 processes are there. Degree of multiprogramming reduced from 100 to 50. So like 50 only presently. So this is done by what? Long term scheduler only. So now whatever a process we are loading into memory, that memory, main memory, that is done by what? Long term scheduler. Is it clear? Everybody please, everybody. Respond. About long term schedule, the points are clear. So one more important point from long term scheduler I am writing. Okay. So to make a system stability, please observe, to make a system stability means there won't be any congestion or contention in the processor or heavy load on the processor, or there is no, suppose sometime no situation may comes, resources may not be utilized properly. So that is the reason we wanted to make the system stable. Okay, we want to make the system stable. So such cases what we do, long term scheduler, select good mix of CP bound and IO bound processes. I hope this point is clear. Is it all of you? long-term scheduler is going to select the good mix of the CP bond by IO bond process. Why, sir? If you only selected only CP bond process meaning what? What is the meaning of CP bond process? CP bond process having the less IO activity, only CPO activity will be more. And if you say IO bond process having what? Less CP work, more IO work. CP bond nothing but is most of the time spending in CPU only. If I only CP bond process selected by the long-term scheduler, so devices not going to be utilized properly. Certain moment it is only select IO bound process, the CPUs may not be utilized properly, IO devices may be busy. To have a proper utilization of every resource, the long-term scheduler should select the good mix of the all type of process so that we can engage all the resources of the computer system. So this is done by what? Long-term scheduler only. So on one line I given, so we wanted to make the system into stable. What is the meaning of stable? See, all the process loaded only, they are not departing. So that need to be controlled. That's what you understand. Degree of multiprogram here, the rate of process creation should be equal to average departure rate of the process. See, certain moment of time, if you create 100 process, other direction process should leave from the system. Otherwise, what happens? There may be more context. So context on CPU or IO devices, right? So process will loaded, other side should be leave from the system. They should terminate. So this balancing should be maintained. The balance should be maintained. That is the reason. Please, now the invocation of the long-term schedule will be lesser than the other processes, because other schedulers frequently they will invoke. But it is only invoke whenever new job you want to load into main memory. Whenever new process want to load into main memory, that moment only long-term scheduler will invoke. So I hope you understand the important points about long-term scheduler. Everybody is clear? Please respond. I need your response, everyone. So now look at the second one. Second scheduler. What is second scheduler? Short-term scheduler. Short-term scheduler. Please. So this generally will present in ready queue, in between ready queue and running state, right? Running state. Okay. Presence will be here, right? Short-term scheduler. What is the functionality? It will select. Okay. It will pick or select. It will select. Okay. Select a process. Okay. Select a process. Process from ready queue and assign to CPU state for execution. So process nothing but what we load? PCB only, ma'am. PCB of a process from ready state we are loading into running state for execution. This is done by. So now short-term schedule invocation is more compared to other scheduler, because frequently whenever you want to load a process into CPU state, that moment it will be invoked here. In the execution frequency or occurrence, invocation of the short-term schedule will be more comparison to other things you understand. Is it clear? Very simple. It presents, I shown in the diagram also. What is the presence here? Here is a presence, pick a process from ready queue and assign to CPU state. That's only duty of a short-term scheduler. It's clear? Third one is a medium-term scheduler. Its functionality very clear, swapping, ma'am. Its functionality is swapping. Okay, swapping means there are two operations: swap in and out. Please understand. In the event of suspension, please understand. In the event of suspension, whenever operating system willing to suspend a process from main memory to secondary memory, now medium-term scheduler invoke, it will suspend a process from memory to secondary memory. Then based on the availability of memory in a main memory, will resume the process. That's what swap out. Swap out means sending into secondary memory. Swap in, so we can bring later into main memory. That need to be understand. So to implement this swapping, definitely hardware support is highly needed. Hardware support is highly needed, please, because we have to send, right? Some hardware support compulsory required. I hope this is clear. So now advantage of medium-term scheduler, sometime if there are heavy load on the process, there are more process available. Long-term storage scheduler loaded more process. Maybe there is some contention to the processor. To reduce the contention, to reduce the burden in the processor, some of the process we can suspend into secondary memory, so that the performance can be improved. Sometimes performance may be low also when you have more process. Clear? So such cases this will invoke, it will suspend the process into secondary memory. The point is clear, all of you. Suspension is not meaning of killing. Killing is different, suspension is killing different. Please understand. Suspension means temporarily process moving into secondary memory, later will bring back to main memory, will execute it. We are not killing a process. Killing means what? Termination killing is different. We are closing the process completely. I hope this is clear. Okay. So now, so there are three things we have discussed. Their presence also I mentioned here. This is all about schedulers. Schedulers. So I said schedule decision making. They're selecting from here or here, here. Then this need to be understand. Fine. So now let us understand the dispatcher. What is the functionality of a dispatcher? Okay. So we'll understand about dispatcher. So dispatcher, please observe. So dispatcher is a component. Okay. Component of short-term scheduler. Please understand, short-term scheduler. Okay. So short-term scheduler. Okay. Dispatcher is a component of a part, some part of a short-term scheduler. Because short-term scheduler, long-term scheduler, mid-term scheduler is there. Dispatch is a component of a short-term scheduler. Simply we can say operating system component also we can tell. The functionality of dispatcher is, please understand, main functional dispatcher is, please understand, context switching. Main functionality, context switching. Context switching, or you understand, mode shifting also done by, so dispatcher, mode shifting, it is also to mode shifting, or as you understand. So whenever a process completes the IO activity, it will come back to ready queue, right? So dispatcher will help to bring a process image, that PCB, from IO state to ready state to begin its execution. So it will jump to the what was the last statement execution was. So we restored the things, you understand. Okay. So main thing was context switching. Okay, context switching done by what? Dispatcher only. Context switching done by dispatcher. What is the meaning of context switching? Can you anybody tell? Yes, can you respond? What is the meaning of context switching? Context switching. Yes. So very simple, understand, process of switching the CPU. Okay, switching CPU will switch. Process switching the CPU from one process to another process. I hope this is clear. Okay. What is the meaning of process switching? So context switching, process of, it is activity of switching. Please understand, it is activity of switching a CPU from one process to other process. So more thing we'll discuss. Lower thing we'll discuss. Please observe. Here is the CPU. Okay. Here is the CPU. Okay. So CPU. Here is like ready queue is there. Here ready queue, right? Ready queue is there. Now see. So very simple. So other way I'll show you. This process P1 is there. Okay. Process P2 is there. Okay. Now see. So now CPU is here. Okay. CPU with what? Process P1. Context switching means like CPU will switches from process P1 to P2. It will leave the P1. It will assign to what? P2. Process will move from P1 to P2. Meaning what? It is leaving the execution of P1 and start the execution of P2. So we'll understand more things. Okay. So process context switching, nothing but please understand, activity will saving. Okay. Saving and loading. Please, saving and loading. Context switching meaning saving and loading the PCBs of processes. PCBs of a process. One process PCB you are saving, other process PCB you are loading. So that detail we'll understand. This line also will detail we understand. Okay. So now please understand. Save. So context switching, again telling save PCB of old process. PCB of old process. old process, PCB of old process, and load saved PCB, saved PCB of new process. So please understand, contest switching time, during contest switch what happens? Save PCB of old process, load the saved PCB of a new process into CP state. So let's try to understand this point clearly. So this is a ready queue, okay? Ready queue, right? Ready queue. So we have a processes. Let's take. So process P1, process P2, process P3 are there, assume that. Here is this running state, right? Yes or no? Running state only, right? Running state. Okay, please. Here is what? Who is there here? Short-term scheduler will be there. That is dispatcher will be there. Okay. So dispatcher. Okay. Dispatcher is worker of short-term scheduler. Okay. So short-term, what functionality? You have to pick a process load. Now see, decision making means, please understand, whenever ready queue have more than one process, whenever ready queue has more than one PCB, now one of the PCB need to be selected. Let's take, we selected what? P1. Okay. So P1 loaded here, no? Dispatch loaded, please understand. See, load PCB of a process P1, load from ready state to running state, loaded. Clear? It is loaded or not? Loaded. Now process P1 executing. Okay. During execution, amount of time given to the process P1 is expired. So time out happen. Still required CPU, but timer what happens? Timer is off. Time expired. Such a case, please understand, now running process forcefully remove from CPU state, sending into where? Ready queue. Another process you have to load. So the process P1 work is not completed, but preemption occurred. Preemption means forceful deallocate the process from running state, right? Now PCB of a process P1, we are loading, saving, na? Save. You have to save the state of a process P1 into memory. So this ready queue. So load. So please understand, load new PCB of a process from ready state to running state. So saving and loading is happening or not? Please tell me, saving and loading is happening or not? Same thing I say, no? Saving and loading the PCB of a process, meaning save PCB of old process. Save it from running state to main memory. You save the state, current state, you save it. Load the saved process, already saved process PCB is there. You load into running state. Now, why we need to save? Can you tell me why we need to save? Because process execution process P1 not completed, right? It has to complete the remaining part. Process should know where it is left off from the last line. So from that point only we have to start. So that you have to save the states. You have the current activity, you have to save PCB value, you have to program counter value, general purpose register value, all we need to save in the PCB, so that later it can start from that point only. So the amount of time taken, please understand, this amount of time taken to contest switching is dispatch latency. Dispatch latency or context switch time or context switch latency also we can tell. Is it clear? Contest switch latency or context switch time or dispatch latency, meaning amount of time taken to perform the context switching between two processes. I hope this is clear. Everyone respond. This line is clear. Contest switching activity is clear. So now this time purely depends on the hardware only, because see, sometime the faster hardware is there, so quickly they can shift it. It depends on the processor also. Now the time completely this also will vary from operating system to operating system and computer to computer system, hardware to hardware also it will vary. So this is pure overhead only. Please understand this important line. Context switch time or dispatch latency is pure overhead. Why, sir? During context switch time there is no useful work done by the processor. CPU is not working anything, right? But busy only, because CPU is ready for execution. I have to load PCB, then only it will start, right? Loading time, no useful work done by the processor, that I want to show. That is the reason this overhead is there. This is contest switch time is overhead purely. So this need to be minimized. That also vary from OS to OS, and computer architecture to architecture also. I hope this is clear. Everyone please respond. Is it clear, right? Okay. Now see, this context switch also two types more. Context switch also two types. One is partial context switch. Partial context switch. Second one is the full context switch. Okay. What does mean full and partial? Suppose, please observe. Only load operation is done. Only load operation done, that we call partial context switch. If suppose save and load happen, then we call full context switch. Example, sir. Example for this. Okay. First process loaded from ready state to running state. During execution, it required IO activity. Okay. IO operation required. You have to save. Before jumping, you say, because you have to come back again, right? You have to go. You are going for IO, nothing, you have to come back. You will remaining. You want to execute it. So you have to, when IO is occurred, you have to save it. When system call is encountered, also you have to save it. Save and load happen. Getting my point? Preemption occur. Preemption due to timers. Timers are high priority. Okay. Such cases, running process need to be forcefully delayed from running state to ready state. Right? You have to save, then you load. Save and load will happen. So now suppose process loaded and execution completed. Simply execution completed, no IO required. Such case only load operation happen. I hope you understand what I am trying to say. One process I loaded into here, executed, terminated. So only load happen, right? Load operation happen. This we call partial context switch. So another time, you know, process I loaded, executing, timer expired, or high priority process encounter, so that you have to send back, save it. IO required, you have to save it. So that is the reason this I think this other things also I explained you. Clear? This all things clear? Everyone respond. So now quickly see will some problems on this process process concepts. Okay. So first question. This question was asked in 2015 paper of set number 3, 1 mark question. The maximum number of processes that can be ready state for a computer system with n CPUs. N CPUs are there. How many processes can be in a ready state? Can you tell me what is the answer? Option A n, option B n square, option C 2 power n, option C independent of n. So let's say n equal to 10 CPUs are there, 10 processes are there. Now how many maximum process can be stay in main memory, ready queue? 10 are there. Is it depends on this n value? Is depends on number of process? No. If single CPU also there, ready queue can contain more defined the capacity of the ready queue. The more number of process depends on number of process you can accommodate in the ready queue or main memory, you understand? Clear? So that's completely independent of this n. Independent. If 1 CPU also there, it can be more. If 10 CPUs also there, it can be more. More means what? Depends on size of the memory, size of the capacity of the ready queue, understand? How many PCBs you can keep it. I hope this is clear. So option D is the right answer. Next question, interesting question. The purely process state transition diagram only. Consider the following statements about a process state transition for a using preemptive scheduling. Preemptive scheduling, multi-programmed with preemptive things is there. Statement, a running process can move to ready state. Is it true? In the last class also I discussed, in the last session I discussed possible transitions from process state transition diagram I discussed. Based on that you can answer it. So a running process can move to ready state. Yes, possible or not? Whenever a preemption is occurred due to time or due to high priority, running process can move. If we require context switching, this under preemptive base, it is possible. True. A ready process can move to running state. We dispatching, true. A ready process, we are moving to running state. We are going to schedule for execution, true. A blocked process can move to running state. This is not possible under multi-program environment. A blocked process, whenever IO complete, any event is complete, the process should go to ready state, not to the block state, because block state is occupied by other process. Sorry. A blocked process can move to ready state. This is possible. 1, 2, 4 is possible. 1, 2, 4. Yes, C. So option C is right answer. Option C is sorry. 1, 2, 4, right. Yeah, option C is right. Look at the another question. Observe and answer it. I hope it is visible. Here is a new state. Here is a new state, ready state, blocked state, running state, and termination is there. So now preemption point also there, no, scheduling preemption also there it is. So which process? A batch operating system, and OS with a preemptive scheduler, OS with a non-preemptive scheduler, a uniprogram. So some options you can eliminate. Non-preemptive, it is a preemptive because see, ready to running, running to ready also there. So in the last class few things I mentioned, see, presence of ready queue always indicate the multi-programmed operating system. So one option we can eliminate, this option D is eliminated. Presence of a transition from running to ready indicate preemptive, so it is not non-preemptive. So that we can eliminate option B also, especially also. It is not batch OS, so obviously we can use a preemptive scheduler only, right? So it is a multi-programmed, so what is what? It is a multi-programmed preemptive based operating system. Presence of ready queue, presence of this transition, we can tell these things. Clear? Chalo, we'll see another question. In the following process state transition diagram for a uniprocessor system, single CPU, assume that there are always some process in the ready state, no, start, new state, this is a new state, ready, running, termination, block state is there. Now first of all I would like to say this is a multi-programmed with a preemptive based operating system. By looking this we can tell, yes or no, because this preemption also there. Transactions are labeled. Let's observe what they are asking here. Now consider the following statements. They given some statements. If a process make a transition D, means terminating, would results in another process make a transition A immediately. So means what? Whenever running process terminated, whenever running process execution completed, terminated, it would result in schedule the another process from take another transition A immediately. Is saying that the moment you terminate the process, immediately you have to load another process into main memory. It is not necessary condition, please. It is immediately may not be happen. Are you getting my point? So transition A, what is the transition A? Start to ready. He is saying that whenever you terminate a process, new process, you have to load it. It's not compulsion. Already some process available in ready queue, they said, some process available. Among the process we can schedule for execution. We can schedule for execution, but he's saying the new process you are loading into memory. So that may not be possible. It is not compulsion. Suppose example, in certain moment of time operating are willing to run 10 process loaded executing. It's not compulsion 11th process should be loaded for execution. Are you getting my point? So a process make a transition D, it would result in another process make a transition A immediately. A immediately not possible. But B is immediately we can tell, because they said already some process available ready state. So always some process available. The moment process goes terminated and running state is free, we can schedule another process. That can be done, but he is saying the loading new process is not necessary. So statement 1 is wrong. Statement B, option B. A process P2 in blocked state, they said no P2 I'm not. It is a blocked state can make a transition E while another process P1 is in running state. So what is saying that a process make a transition E means what? Block to running state process P2 is moving while another process P1 is running in CPU. This possible or not? See, whenever, please understand, whenever running process required IO, it will come for IO, other process will schedule it. Whenever IO complete, it can go for ready state. It can go for ready state while it is executing other process. It is completely possible. Completely possible. So option B is right. Option C, preemptive scheduling. Option C is preemptive scheduling. Yes, it is a preemptive scheduling. Non-preemptive, it is not a non-preemptive, it is a preemptive. See, transition is present from running to ready, indication preemption. So now what I can say, option B and C both are right. MSQ type question. Both are right. Option B, say both are right, ma'am. So we can answer like this. So I hope you understand the things. So now, so in this session we have discussed like various, again I given various scheduler, their functionality and dispatcher, various types of queues, the presence of the queues also, and implementation part also we observed. In the upcoming class, I will be starting from the operating system is a CPU scheduling or process scheduling. So thank you so much for watching this video. I will come up with another video because I already given a schedule also. Most of the important topic I would like to cover from the operating system. So kindly tune to this channel. Thank you so much.